Pluto, a far-off and enigmatic celestial object, was once regarded as a full-fledged planet in our solar system. It held a position as a key member of our planetary system until recent groundbreaking statements by renowned astrophysicists Neil deGrasse Tyson and Michio Kaku reignited interest in Pluto. These distinguished scientists have proposed an astonishing idea that Pluto might be headed toward a catastrophic encounter with Neptune. But how could such an incredible event transpire, and what could the repercussions of such a colossal impact be? Are we witnessing an extraordinary anomaly in the cosmos? Or is there more to this potential cosmic event than we initially perceive? Join us as we examine the possible outcomes of a hypothetical Pluto-Neptune collision. Initially classified as a planet, Pluto was later redefined as a dwarf planet, but continues to intrigue astronomers and scientists, sparking curiosity throughout the vastness of space. Investigations carried out by leading experts in the field of space science suggest that Pluto's orbit dangerously brings it close to Neptune's. Well-known astrophysicists like Tyson and Kaku have raised alarms about the potential hazards posed by a collision between these two celestial objects, warning that such an event could pose risks to Earth as well. But what would it take for such a catastrophic occurrence to happen? Pluto's orbit around the Sun is notably different from that of other planets. It requires an astonishing 248 years to complete one full revolution, meaning that since its discovery in 1930, Pluto has yet to finish even a single orbit around the Sun. Yet, the intrigue surrounding Pluto's motion does not stop there. Its orbit is characterized by an eccentric shape, quite unlike the near-circular paths of the major planets. Additionally, Pluto's orbit is tilted at a 17 degrees angle relative to the plane of the solar system, making its path significantly more erratic in comparison to other planets. This orbital peculiarity introduces a layer of unpredictability to Pluto's motion, complicating our understanding of its behavior. An especially fascinating aspect of Pluto's orbit is its interaction with Neptune. During certain periods of its orbit, Pluto actually crosses inside Neptune's orbital path, defying expectations based on their expected positions within the solar system. This raises an obvious question. Why has Pluto never collided with Neptune despite their intersecting orbits? The answer lies in the gravitational interactions of other celestial bodies within the solar system. Following Pluto's discovery, astronomers were initially puzzled by the peculiar shape of its orbit. Unlike the relatively flat orbits of most planets, Pluto's path stood out due to its steep inclination and highly irregular shape. This mystery was addressed through a concept called the three-body problem in celestial mechanics, which attempts to understand the movements and interactions of three celestial bodies: Pluto, Neptune, and the Sun, all under their mutual gravitational influence. This concept is similar to predicting the future positions of these objects based on their current locations and the forces acting upon them. When applied to Pluto's situation, the three-body problem explains how the Sun, Neptune, and Pluto interact in a highly intricate manner. Key terms such as libration, oscillatory libration, and VSK wobbling play a significant role in solving this puzzle. Astrophysicists suggest that the relative stability of planetary orbits may be attributed to a phenomenon called libration. Specifically, when Pluto crosses Neptune's orbit, the relative positioning of the two bodies is offset by approximately 90 degrees, which plays a critical role in preventing their orbits from aligning and leading to a collision. Libration, which refers to the oscillation of an object in its orbit, ensures that Pluto remains well above the plane of the orbits as it nears Neptune or other large planets, thus offering protection against potential collisions. Another factor maintaining Pluto's orbit is the VSK wobbling, named after the researchers who initially explored the movement of objects in space. The VSK wobbling describes how the gravitational forces between Pluto, Neptune, and the Sun influence the motion of each object, ensuring Pluto's orbit remains stable even as it follows an unconventional path. This sophisticated gravitational interaction helps preserve the stability of Pluto's orbit over long periods, despite the apparent chaos of its path. The three-body problem is central to understanding how celestial objects interact, providing insights into Pluto's motion and helping astronomers predict the behavior of distant stars, planets, and other celestial bodies. Mathematical simulations from the late 1980s revealed that even though Pluto's orbit is highly irregular, its trajectory remains relatively stable, with only small deviations from its initial conditions. These steady characteristics of Pluto's orbit have persisted over time, allowing astronomers to refine their models of its motion. Recent computer simulations have also clarified how large planets such as Neptune, Jupiter, and Saturn impact Pluto's orbit. One unique feature of Neptune's relationship with Pluto is their orbital resonance, a 2-to-3 ratio, where for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance helps stabilize Pluto's orbit and prevents a collision. However, Neptune's gravitational influence is not the only factor at work. Jupiter's immense gravitational pull also plays a substantial role in keeping Pluto's orbit stable. In addition, Saturn's gravity provides further stability to the outer reaches of the solar system. Studies suggest that Jupiter's massive gravitational field alone is sufficient to maintain the stability of Pluto's orbit for billions of years, possibly ensuring that it remains on its current trajectory indefinitely. Together, Neptune, Jupiter, and Saturn work in unison to prevent Pluto's orbit from becoming unstable, contributing to the overall stability of the solar system. Without these forces, the cosmos would be much more chaotic, with objects like Pluto potentially colliding with other bodies or being ejected from their orbits, causing significant disruption throughout the universe. Understanding Pluto's orbital dynamics is particularly important, especially as speculation about a future collision with Neptune grows. The intricate relationship between Pluto's orbit and Neptune's offers valuable insights into how neighboring planetary systems interact. Pluto's case illustrates how even orbits that seem highly erratic can reach stability due to the complex gravitational interactions at play. Studying Pluto's orbit highlights the necessity of ongoing observation to ensure our understanding of the universe remains current. Exploring space often brings us face to face with the strange and unpredictable nature of celestial objects. Pluto's orbit exemplifies this unpredictability, showing how even the most chaotic systems can maintain a stable course due to gravitational forces. The 2:3 orbital resonance between Pluto and Neptune is a critical feature of this system, ensuring that despite their intersecting paths, the two bodies avoid a collision. This gravitational relationship is a cornerstone of celestial mechanics, demonstrating that even the most irregular orbits can achieve harmony over time. In addition to Neptune's influence, other massive planets such as Jupiter, Saturn, and even Uranus play significant roles in maintaining the equilibrium of the solar system. Jupiter's vast gravitational field serves as a protective force, keeping smaller objects like Pluto on course. Some researchers speculate that Jupiter's gravity might have even prevented Pluto from being ejected from the solar system, further emphasizing the importance of understanding the gravitational dynamics within our solar system. While Pluto's orbit remains stable for now, it's important to recognize that changes could occur in the distant future. Astrophysicists like Neil deGrasse Tyson continue to probe the cosmos, uncovering deeper insights into the forces that govern the movement of celestial bodies. Although the likelihood of a Pluto-Neptune collision remains low, the very possibility of such an event serves as a reminder of the ever-changing nature of the universe. It underscores the importance of continued exploration to expand our knowledge of the forces shaping our solar system. As the study of Pluto's orbit and its interactions with other celestial objects progresses, it remains crucial for advancing our understanding of the broader universe. Pluto's situation serves as a case study for the complexities of orbital resonance, where the movements of celestial bodies are intricately linked. The 2:3 orbital resonance between Pluto and Neptune ensures that despite their intersecting paths, the two bodies never collide. This gravitational balance has preserved Pluto's orbit for billions of years, illustrating how forces within seemingly chaotic systems can lead to stable, predictable outcomes. The importance of this resonance cannot be overstated. It represents a fundamental principle of celestial mechanics, proving that even complex orbital behaviors can achieve harmony through gravitational forces. Understanding orbital resonance goes beyond the relationship between Pluto and Neptune, shedding light on the broader dynamics of the solar system. The interactions between planets, dwarf planets, and other celestial bodies are essential to maintaining the stability of our solar system. Jupiter plays a critical role in this process. Its enormous gravitational influence acts as a safeguard for smaller bodies like Pluto, preventing them from deviating too far from their established paths. Jupiter's gravity also extends beyond Pluto, impacting the orbits of asteroids, comets, and other small objects in the outer solar system. This interconnectedness highlights the role of gravitational forces in preserving balance within the solar system. Some researchers even hypothesize that Jupiter's gravitational force may have helped secure Pluto's position in its current orbit, preventing it from being ejected from the solar system. This further reinforces the concept that each planet plays a specific role in maintaining the solar system's overall structure. Studying Pluto's orbit and its gravitational interactions with other planets sheds light on the dynamic nature of space. While mathematical models and simulations offer valuable insights into celestial mechanics, they also reveal the inherent uncertainty of predicting long-term motions. Small changes in initial conditions or minor deviations in gravitational forces can lead to vastly different outcomes over time, highlighting the complexity and unpredictability of space. This uncertainty reinforces the necessity for ongoing observation and analysis. Studying systems like Pluto's provides vital lessons about the forces that govern the motion of celestial bodies. Pluto's orbital stability, despite its irregularities, underscores the power of gravitational forces and the self-regulating nature of orbital mechanics. As space exploration progresses, it becomes increasingly evident that understanding the delicate interplay of these forces is key to uncovering the broader dynamics that govern both our solar system and the universe at large. As research into Pluto's orbit and its interaction with other celestial bodies continues, it sheds light on the fundamental principles that govern the solar system's behavior. The fact that Pluto has maintained its orbit for billions of years, despite its seemingly erratic path, highlights the extraordinary nature of gravitational interactions. These interactions help preserve cosmic order, even when objects like Pluto appear to follow unpredictable trajectories. The importance of maintaining this balance cannot be overstated, as it plays a critical role in preventing catastrophic events within our solar system. Additionally, the ongoing study of Pluto's orbit underscores the complexity of space exploration and the need for constant monitoring. While Pluto's trajectory appears stable today, future shifts in gravitational influences could lead to unexpected changes. Astrophysicists, including Tyson and Kaku, continue to emphasize the interconnectedness of celestial objects and how understanding these relationships is crucial for predicting the future of our solar system. They argue that even small gravitational disturbances can have significant long-term effects, highlighting the delicate nature of cosmic balance. One of the most intriguing aspects of the ongoing study of Pluto's orbit is how it exemplifies gravitational resonance in action. The 2:3 orbital resonance between Pluto and Neptune clearly illustrates how two objects can share overlapping paths without colliding, thanks to the stabilizing forces at play. Such resonances are not unique to Pluto and Neptune. Similar relationships exist between other planets and their moons, as well as between asteroids and other objects within the solar system. These orbital resonances help prevent chaos by ensuring that celestial bodies remain on their designated paths without interfering with one another. Moreover, Jupiter's role in stabilizing Pluto's orbit cannot be overlooked. With its massive gravitational field, Jupiter acts as a stabilizing force, ensuring that Pluto and other objects remain on their trajectories. Jupiter's influence extends well beyond Pluto, affecting many bodies in the outer solar system. Its role in stabilizing the solar system emphasizes the interconnectedness of these massive celestial objects. Without Jupiter's gravitational influence, Pluto's orbit might have been more vulnerable to disruption, possibly even resulting in its ejection from the solar system. This further reinforces the idea that the solar system operates as a finely tuned system, with each planet and moon playing a specific role in maintaining overall stability. While these gravitational interactions help keep the solar system balanced, they also raise important questions about the long-term evolution of planetary orbits. The fact that Pluto's orbit remains largely unchanged, despite its erratic nature, speaks to the self-regulating mechanisms of celestial mechanics. However, this stability is not guaranteed, and even minor changes in the gravitational forces acting on Pluto could alter its trajectory. This possibility highlights the importance of continued observation and modeling to understand the forces shaping the future of the solar system. The ongoing study of space, especially by scientists like Tyson, provides deeper insights into the behavior of celestial bodies. Their work helps refine our understanding of orbital mechanics and predict the future movements of planets, moons, and other objects. These predictions are invaluable, offering insight into the dynamics of the solar system and beyond into the wider universe. By studying objects like Pluto, scientists can observe how gravitational forces govern the motions of celestial bodies over vast periods, revealing the interconnectedness of the universe. Furthermore, the potential for changes in Pluto's orbit in the distant future, whether due to shifts in gravitational forces or other unforeseen factors, reminds us of the unpredictable nature of space. Even the most stable systems can undergo changes over time. As we continue exploring the cosmos, we must remain open to new discoveries and acknowledge the limitations of our current understanding. In this context, while the chance of a Pluto-Neptune collision seems remote, it serves as a reminder that cosmic events can unfold in unexpected ways. The possibility that Pluto's orbit might change after billions of years of stability illustrates the ever-evolving nature of the universe. As astrophysicists continue to push the boundaries of our understanding, they highlight how gravitational interactions can both stabilize and potentially disrupt the paths of celestial bodies. The complexities of Pluto's orbit offer an intriguing glimpse into the dynamics of space. By studying the interactions between Pluto and Neptune, scientists gain a better understanding of the forces that shape not only our solar system but other planetary systems throughout the universe. These insights help us appreciate the delicate balance that governs the motion of celestial bodies and the ongoing processes that influence their behavior. They also stress the importance of continued research and exploration as our understanding of space is always developing. In conclusion, Pluto's orbit, with its complex interactions with Neptune, Jupiter, and other planets, serves as a prime example of how gravitational forces shape the solar system. While Pluto's orbit remains stable for now, the ongoing study of its trajectory reveals the complexities and uncertainties that govern the universe. The potential for a future Pluto-Neptune collision, though improbable, reminds us of the dynamic and ever-changing nature of space. Studying Pluto and other celestial bodies deepens our understanding of the forces at work in the cosmos, helping us predict the future behavior of planetary systems and ensuring that our knowledge of the universe continues to expand.